What if I told you the atoms making up your body each carry tiny magnetic moments, but most of them cancel so you don't end up clinging to the fridge? That's not science fiction. That's just how physics runs on Tuesday. Magnets only exist because electrons act like they're desperate to stand out from the crowd. And here's the 2025 curveball. Researchers just merged two exotic materials into atomic sandwiches that revealed strange magnetic behaviors scientists think could power future quantum sensors and maybe even qubits. In this video, I'll explain why Earth acts like a magnet, where electrons get their weirdness, and why these new discoveries actually matter. But first, if most ordinary stuff isn't magnetic, then how does an entire planet act like a gigantic refrigerator magnet? So why is the Earth basically a giant magnet? The answer starts not at the surface, where rocks and oceans show no obvious sign of magnetism, but deep inside the planet. Hidden far below the crust lies the outer core, a vast layer of molten iron mixed with nickel that never stops moving. And it's that restless motion, not the solid material itself, that produces Earth's magnetic field. Think of the outer core less like a calm reservoir and more like a roiling sea. Immense heat left over from Earth's formation and boosted by radioactive decay keeps this liquid iron in constant circulation. Add the planet's daily rotation and the flows are twisted into spiraling organized patterns. These swirling currents carry electric charges, and physics tells us that electric currents create magnetic fields. On a planetary scale, these reinforce each other into a self-sustaining system scientists call the Geodynamo. It's not atoms sitting still in alignment like in a fridge magnet, but a whole ocean of liquid metal in motion, powering a planetary-scale electromagnetic engine. That geodynamo has been active for billions of years, and its influence extends far into space. Earth's magnetic field creates a shield that deflects charged particles streaming from the sun. Without it, the planet will be far less protected from solar wind, which can gradually strip away atmospheres. Mars, for example, lost much of its atmosphere after its own dynamo shut down. Here on Earth, the field is one of the reasons our air and oceans remain intact. Still, Earth's magnetism doesn't act like a steady bar magnet frozen in space. Because it's driven by constantly changing currents in the core, the field itself shifts over time. Magnetic poles drift, tilt, and occasionally even reverse completely. In fact, geological evidence captured in cool volcanic rock shows that Earth's field has flipped polarity many times in the past million years. The drifting is not just a curiosity, it makes a practical difference in how we navigate. For centuries, explorers and sailors tracked the slow wander of the poles, but in modern times the motion has become much faster and more closely monitored. In the 2000s, the North Magnetic Pole surged forward at speeds of up to about 55 kilometers per year as it left Canada and moved towards Siberia. More recently, however, data from the 2025 model updates show that its pace has slowed to roughly 35 kilometers per year. That's still fast on a geologic timescale, but it illustrates that the motion is irregular, picking up and slowing down depending on what's happening deeper inside the core. Because navigation depends so heavily on knowing where magnetic north is, scientists produce regular updates to the World Magnetic Model every 5 years. Each new release recalibrates systems ranging from ship and aircraft instruments to GPS corrections and even compass apps and smartphones. Without those updates, cumulative errors would slowly build across global navigation. The 2025 version of the model added the most detailed resolution yet, WMMHR 2025, helping account for finer changes in the field. And updates don't just adjust for drifting poles. Near the magnetic poles themselves, the field plunges steeply into the ground, making compasses unreliable. These regions are known as blackout zones, and the World Magnetic Model marks them out clearly for aircraft, ships, and anyone attempting polar travel. They are reminders that Earth's invisible shield, while stable enough to live under, is constantly shifting and comes with places where ordinary tools no longer work reliably. The drifting and shifting poles highlight that Earth is more like a rechargeable dynamo than a static magnet. The signals we detect on the surface, compasses pointing, auroras shimmering, are just the outward signs of an engine churning non-stop thousands of kilometers below our feet. And unlike a permanent magnet, this dynamo can wobble, drift, or even reverse entirely. Each outcome depends on how the molten metal organizes itself as it keeps circulating. It's a striking reminder of how dynamic the planet really is. We might think of Earth as rock solid, but in reality it's powered by a vast system of liquid metal in motion. That moving core drives a field that stretches tens of thousands of kilometers into space, shaping conditions for navigation, shielding the atmosphere, and even controlling how we think of direction at the surface. And speaking of direction, there's an odd detail hidden in the way we use compasses every day. The arrow we call north doesn't actually point to the Earth's north magnetic pole at all, but something else entirely. And that twist in terminology is where Earth's magnetic story gets even stranger. North loves south, but wait, it's backwards? Compass needles are labeled north-seeking, which means the tip we call north is actually drawn toward Earth's magnetic south pole, the one that currently sits up near the geographic North Pole. It's counterintuitive, but that's a convention we've inherited. Every time you check a compass, what it's really doing is pointing you toward a magnetic south that happens to align closely, though not perfectly, with the top of our planet. At first glance, this looks like a simple mix-up that could have been fixed long ago by just renaming the poles. But the convention stuck early, back when navigation first relied on compasses, and by the time the scientific details were clarified, maps, globes, and textbooks were already standardized. Changing everything would have caused more confusion than consistency. So what started as a human naming choice ended up framing the way we still talk about directions today. In other words, the names don't reflect the physics, they reflect history. Once you know this, the slightly messy nature of navigation begins to make sense. Because labeling aside, Earth's magnetic poles also don't stay fixed in place. They wander across the surface in response to the liquid metal flows deep in the outer core. For centuries, the poles shifted slowly enough that explorers could rely on gradual updates to maps, but more recent decades have seen the poles drift much faster. In the 2000s, the North Magnetic Pole accelerated to around 55 kilometers per year, before slowing to roughly 35 kilometers per year in the early 2020s. Even that slower pace still means the magnetic landmark your compass points to today is hundreds of kilometers removed from where it was for previous generations. This constant motion is the reason we have to distinguish between true north, the fixed point marking Earth's rotation axis, and magnetic north, the moving target your compass needle chases. The difference between those two is called magnetic declination, and it varies depending on where you stand. Cartographers regularly redraw declination lines so maps remain useful, and the World Magnetic Model is the shared reference that global navigation systems rely on. Every 5 years, scientists release an updated version so that ships, aircraft, smartphones, and surveying equipment keep pointing where they should. If these updates didn't exist, the errors would build up steadily, making long-distance travel and even basic navigation inaccurate over time. Those updates matter far beyond hikers or outdoor adventurers. Airlines and military groups use magnetic headings daily, and so navigation software and databases must be recalibrated with every revision of the model. A compass needle may look like a simple piece of metal, but the data behind how we interpret its direction is constantly maintained on a global scale. Without those corrections, courses that once matched magnetic bearings could drift farther from reality each passing year. For everyday use, the wandering pole means the compass in your pocket app or traditional handheld device isn't pointing at a north that's timeless. It's pointing at a moving signal created by the Geodynamo in Earth's core. That's why historical navigation logs sometimes show small discrepancies in bearing. The magnetic north of the past occupied a slightly different position than it does today. A hiking route recorded 50 years ago near Hudson Bay, for instance, would point a compass toward a destination now located hundreds of kilometers away from today's north-seeking direction. The maps might look similar, but the invisible field guiding the needle has drifted beneath them. This shift in magnetic environment also shapes the lives of organisms that rely on magnetism for orientation. Migratory birds, sea turtles, and even some insects use magnetic cues to guide their journeys. As the poles move, the signals that these animals evolve to follow change as well, which means migratory patterns can subtly adjust over generations. This is one reason scientists track pole movement so carefully. It doesn't just matter for compasses and satellites. It directly influences the biology of species that depend on the magnetic field as part of their internal navigation systems. All of this, the mismatched labels, the erratic pole motion, the animal migrations, illustrates the same truth. Earth's magnetism is not a fixed or tidy system. It's produced by a dynamic planet with a restless core, and we interpret it through human conventions that don't always match the underlying reality. The north end of your compass is guided by a south magnetic pole drifting through the Arctic, and our maps and navigation tools are constantly catching up to that motion. To humans, it's nothing more than a bureaucratic update every few years, but to the planet itself, it's just a normal churn of liquid ion currents far below. And yet the compass never falls out of favor. Despite the backward naming and shifting reference points, a needle will always align with the invisible field lines pulling at it. The tool works, even if the terminology is off. That reliability is why we continue to rely on it, layering technology and models on top of what's essentially a small piece of magnetized metal swiveling in response to Earth's restless dynamo. This brings up an even bigger question. The compass keeps working for the same reason magnets in general work. They respond to the magnetic fields hidden in matter. But if Earth itself is magnetic and every atom contains electrons that behave like tiny magnets, why doesn't everything around us stick together as one huge clump? The answer lies in the surprising behavior of the tiniest building blocks of matter, the secret magicians inside every atom. Every atom around you hides a surprising trick. At its heart sits a nucleus, and surrounding it are electrons that don't follow neat little planetary paths, but instead exist as hazy probability clouds. You can't say exactly where an electron is at any given moment, only where it's most likely to be. And yet each of these electrons comes with an intrinsic property called spin. Spin isn't a literal rotation the way a top spins. It's a fundamental quantum characteristic, something built into the electron itself. That spin gives rise to a tiny magnetic moment, making every electron act like the smallest imaginable bar magnet. When you add up the countless electrons inside even a speck of dust, you might expect overwhelming magnetism. But the world clearly doesn't work that way. Most matter stays magnetically quiet. The quiet comes down to pairing. In atoms, electrons occupy shells and orbitals, and the rules of quantum mechanics, especially the Pauli exclusion principle, force them into arrangements where no two electrons can share the exact same state. As those orbitals fill, electrons tend to arrive in opposite spinning pairs. One goes up, the other down. Their magnetic moments oppose each other so precisely that the effects cancel out. It's like two people singing the same song in opposite keys. Instead of getting louder, the sound dissolves into a flat silence. That cancellation is why your desk, your phone, or your body doesn't suddenly leap toward the nearest refrigerator magnet. But electrons don't always have partners. When orbitals are half-filled, some electrons remain unpaired, and their magnetic voices don't get canceled. Those unpaired spins create atoms that carry a net magnetic moment. The atoms of iron, cobalt, and nickel are the most famous examples. Their electronic structure leaves room for several unpaired electrons, which means each atom acts like a tiny, uncompensated magnet. One of these mini-magnets is still unimaginably weak. But in materials where the atoms can line up their unpaired spins in the same direction, the affect compounds, and suddenly you get fields powerful enough to attract paperclips, swing a compass needle, or anchor the memory in your phone's hard drive. Iron is the classic case. Each of its atoms carries multiple unpaired electrons, all aligned contributions that reinforce one another. That's why magnets throughout history have been linked so strongly with this element, whether in natural lodestone, industrial machinery, or the hidden movement of Earth's molten core. Nickel and cobalt, just next door on the periodic table, share arrangements that leave their spins unsatisfied as well. Their unpaired electrons also combine into robust magnetic properties, letting them join iron as the building blocks of most practical magnets. Meanwhile, metals like copper, silver, and gold sit with filled valence shells. Every electron has a partner. The paired spins wipe each other out, leaving the atom with almost no net magnetic moment. Hold a gold ring up to a strong magnet and nothing dramatic happens. It may as well be invisible to the field. Aluminium offers another example. Tightly paired spins and completely filled outer orbitals prevent any lasting magnetism, even though the metal's conductivity makes it behave in other fascinating ways. The difference isn't the presence of electrons, they all have plenty, it's how nature arranges them. Now, the role of structure makes things even more subtle. Consider stainless steel. It's built mostly from iron, yet not. Every form of stainless steel is magnetic. That's because atoms don't just exist in isolation, they assemble into large repeating lattices. If the crystal arrangement lines up the iron atoms so their spins reinforce one another, the result can be strongly magnetic. But if the structure forces spins into opposed orientations, the contributions cancel. That cancellation explains why one spoon clings to your fridge while another, made of almost the same elements, refuses to react at all. The ingredient list is important, but the microscopic geometry is equally decisive. This is part of what makes magnetism seem paradoxical. On one hand, the property comes from a universal source. Every electron has spin, and that spin generates a magnetic moment. You cannot find an atom without this trait. On the other hand, most matter shows no magnetism at ordinary scales because the system balances itself so well that the effects vanish. In everyday life, you only notice magnetism in a handful of materials, yet those materials work precisely because they break the balance in just the right way. You can see it as a kind of vote. In most atoms, paired electrons vote in opposite directions, tallying out to zero in the overall count. Certain atoms with unpaired spins deliver a surplus of votes all in the same direction. Stack millions of those votes together inside a crystal, and you begin to see how macroscopic magnetism can emerge from invisible quantum rules. In iron, the combined signal is strong enough to persist across chunks of solid metal, giving humanity tools to create compasses, dynamos, and electric motors. Without that lopsided vote in favor of one spin orientation, technology would look completely different. That's the strange mix. Omnipresent at the microscopic level, rare at the macroscopic level. Every object you see conceals countless spinning charges, but only a few arrangements allow their voices to rise above cancellation. These exceptions shape human history, from the first compasses guiding ships across oceans to the intricate magnets etched into the chips inside your computer. The ability to exploit unpaired spins gave us control over a force otherwise hiding in plain sight. And yet, even when atoms do hold unpaired spins, whether those tiny magnets transit into a noticeable field depends on their surroundings. A single iron atom carries its magnetic moment no matter what, but pack iron atoms together in random orientations and the crowd gets noisy again. To create visible magnetism, many spins must not only exist unpaired, but also align with one another on a larger scale. Without that cooperative alignment, the atomic voices cancel out as effectively as paired electrons within a single atom. That's why magnetism in real materials is layered with complexity. It has an atomic ingredient, the existence of unpaired electron spins, and it has a collective ingredient, the way those spins point relative to each other in the material. If either element is missing, macroscopic magnetism disappears. Atoms may be tiny magicians, but the stage they stand on matters just as much as the trick itself. Understanding this dual requirement helps explain why some common objects seem dull to magnets while others unexpectedly surprise you. The key isn't only what kind of atoms they're made of, but how those atoms are arranged and whether their magnetic moments are allowed to cooperate. This sets the stage for some of the strangest results in ordinary life. A spoon that seems unmagnetic until it suddenly reacts, or a material that behaves inconsistently depending on how its microscopic neighborhoods are structured. And that puzzle, why something that looks so ordinary can reveal hidden magnetism depending on how its inner pieces align, points directly to another layer of the story that lives not in single atoms but in the collective architecture of matter itself. Invisible magnetic architectures around us. Take an ordinary stainless steel spoon. Most of the time, it sits there without any sign of magnetism. It doesn't stick to the fridge, and it doesn't interfere with a compass, but press it against a strong magnet, and suddenly it clings as if it belonged there all along. What just happened? That temporary stickiness isn't magic, it's the effect of hidden structures inside the metal known as magnetic domains. These domains are tiny regions within a material where the magnetic moments of atoms already aligned. Inside the spoon, countless domains exist, but they're all oriented in different directions, canceling one another out and leaving no net magnetic field. Zoom into the microscopic scale, and you see clusters of spins lining up in neat groups, each one pointing its magnetism a certain way. Right beside them, another patch of atoms faces an entirely different direction. Step further, and you'll find yet another cluster aimed sideways again. To the outside world, it looks neutral, but within the material there's a quiet standoff among these tiny magnetic neighborhoods. The result is a spoon that behaves as if nothing magnetic is going on, even though its atoms are busy lining up internally. The trick comes when you bring in a strong external magnet. Suddenly those hidden neighborhoods feel pressure from the outside field telling them which way to lean. Some domains rotate to match the external field, and because enough of them switch sides, the whole object shows a net attraction. That's when your spoon snaps against the magnet. Pull the magnet away, however, and the pressure disappears. With no outside field keeping them in order, many of the domains drift back into random directions, and the overall magnetism fades once again. This idea explains why most metallic objects around us act non-magnetic until they encounter a strong enough field. Their atoms never lost the capacity for magnetism, but the domains cancel each other unless an external influence aligns them temporarily. For magnetism that sticks around without constant encouragement, something extra must happen. In practical terms, permanent magnets are simply materials whose domains have been locked into a unified direction. Usually, this is achieved by heating the material near its Curie temperature, where atomic groups move freely, and then applying a strong external field. As the material cools, the domains freeze in alignment, and that lock-in remains even when the outside field is gone. You can see hints of this process in simple experiments. Wrap a coil of wire around an iron nail and run current through the wire, and the resultant magnetic field pushes the nail's domains into alignment. As long as the current flows, the nail acts like an electromagnet. Even after the current is switched off, part of the induced alignment can linger, leaving the nail weakly magnetized. This persistence is precisely why rubbing a nail with a magnet can give it a lasting north and south. Domains that were once scattered now remember the training they've been given. Engineers rely on this principle constantly. Materials that allow their domains to flip easily back and forth, such as certain steels, are chosen to make electromagnetic cores that need to be switched on and off with current. Other harder materials, once aligned, resist returning to randomness, which makes them ideal for permanent magnets used in machines, electronics, and speakers. Whether a magnet holds its strength or lets go quickly depends entirely on how cooperative its domains are and how firmly they can be locked into alignment. The same logic explains why not all stainless steel spoons behave the same way. Stainless steel is not a single recipe. It's a family of alloys created by mixing iron with chromium, nickel, and other elements. In some versions, the crystal arrangement of atoms allows iron spins to align when exposed to a strong field. In others, the specific arrangement suppresses this ability almost completely. The variant known as austenitic stainless steel, commonly used in cutlery, has a crystal structure that prevents domains from aligning, so it usually won't stick to a fridge magnet. On the other hand, ferritic or martensitic stainless steels with slightly different structures can support domain alignment and will snap onto a magnet with ease. The difference isn't a contradiction in physics, it's a reflection of how microscopic structures and alloy composition control whether domains reinforce or cancel. Understanding domains also changes how you think about the magnet-object interaction itself. When you bring a magnet close to iron, it's not simply pulling passively. The external field is actively rearranging the domains inside the iron, tipping the balance so that countless tiny regions swing to the same side. What looks like an invisible tug is really millions of atomic neighborhoods reorganizing in real time. The stronger the external field, the greater its command over those domains, and the more convincingly the object locks into place. At this point, someone might picture domains like battle lines that just need a commander calling them into order. That picture works well enough, but it's most important to remember that the affect is collective. No atom alone creates the powerful attraction we experience. It's only when the clusters synchronize that their individual magnetic fields add up to something noticeable. A permanent magnet, then, is just a piece of matter where human intervention has forced most of those clusters to lean the same way, permanently freezing them into cooperation. The implications are practical. From the easiest refrigerator magnet to the most advanced electric motor, the effect stems from the same principle: organizing domains. Devices like MRI machines, transformers, and hard drives don't rely on new exotic particles. They rely on careful management of how domains flip, align, and sometimes resist alignment. The physics remains the same whether you're picking up paper clips with an iron nail or rotating turbines with magnets the size of truck wheels. What feels remarkable is that none of the atoms themselves actually change. Every electron retains its spin. Every atom contributes the same quantum property. The entire distinction between a dull lump of metal and a powerful magnet lies in whether its internal domains are arranged in harmony or left to cancel one another out. Magnetism on this scale is less about ingredients and more about organization, the choreography of millions of small participants aligning into one voice. This perspective naturally raises another question. If magnetism in materials comes down to the alignment of countless electrons, then how do individual electrons carry that magnetic potential in the first place? What is it about an electron, just a single subatomic particle, that makes it behave like a tiny bar magnet at all? To answer that, we have to step beyond domains and crystal structures and revisit what electrons actually are. And here is where things take another strange turn. Many of us were taught to picture them as little planets orbiting a nucleus. That picture, though, hides the true quantum reality. Electrons don't orbit, they teleport. Electrons don't orbit, they exist in probability clouds. That's a strange truth at the foundation of modern physics. Instead of zipping around a nucleus on predictable tracks, electrons occupy fuzzy zones where the best you can say is the chance of locating one in a given region. These clouds, called orbitals, show up as spheres, dumbbells, or more intricate patterns depending on the atom. They aren't paths, they're likelihoods. An electron doesn't swing around like a marble in orbit. It simply exists as a spread-out possibility until a measurement forces it to appear somewhere definite. This perspective feels alien compared to everyday experience. We assume objects must have precise locations. A thrown baseball doesn't dissolve into a cloud and then reassemble when caught. But electrons ignore that rule. At the atomic scale, certainty gives way to probabilities. What's remarkable is that despite this uncertainty, materials built out of electrons behave consistently. Metals conduct electricity, magnets hold their fields, and atoms form stable bonds. Fuzzy positions don't produce fuzzy matter. The order we see around us somehow rises out of this apparently uncertain world. Now add another layer. Electrons come with a built-in form of angular momentum known as spin. Spin is a miniature version of a ball twirling on an axis. Electrons aren't tiny spheres, and nothing physical is whirling inside them. Spin is a fundamental quantum property. You can think of it like a label attached to every electron, an intrinsic characteristic that doesn't depend on whether the electron is in motion or at rest. That label has measurable consequences. It generates a magnetic moment. Each electron produces its own tiny magnetic field, making it act as though a North Pole and a South Pole are embedded within it. One of the earliest and clearest demonstrations of this came from the Stern-Gerlach experiment in 1922. Scientists fired silver atoms through a non-uniform magnetic field, expecting, according to classical physics, a smooth spread of deflections, like marbles rolling off in a range of angles. Instead, the atoms neatly split into two groups. The result was unmistakable. Electrons don't display a continuum of orientations, but only two distinct possibilities. Their spin behaves as a binary choice, often described as up or down. This was evidence that spin is quantized, restricted to specific values rather than a sliding scale. That discovery remains central to understanding magnetism today. The magnetic strength of ordinary materials doesn't come from electrons orbiting their nuclei like currents in wires. It comes from spin. The probability cloud may blur where an electron is found, but the magnetic dipole created by its spin is stable and consistent. Multiply that dipole by the trillions of electrons packed into a material, and you can see how atoms add up to form the macroscopic magnets we rely on. It might feel contradictory. Electrons behave unpredictably in space, yet carry a reliable magnetic identity. But that duality is exactly what nature gives us. The randomness of position doesn't undermine the fact that every electron contributes a permanent magnetic moment. When enough of those moments align, you get the strong, persistent magnetism of a bar magnet. The atom-level weirdness doesn't vanish. It simply expresses itself through order when collective alignment takes over. This also explains why magnets are so robust. You can leave one in a drawer for decades, and it will still work. Its electrons don't need to trace neat orbits for the magnetism to survive. Instead, the permanence lies in unpaired spins that stay aligned in a solid structure. Movement is irrelevant, the property is intrinsic. Magnetism in this sense isn't generated by orbital mechanics, but by the very nature of the particle itself. There is, however, a limit to how familiar we can make this sound. Ask why electrons have spin, and the honest answer physics offers is that they just do. Spin is not built out of smaller mechanisms that we've uncovered. It isn't explained by hitting gears or actual rotation. It is an observed property, tested countless times in experiments, encoded in the equations of quantum mechanics, and essential for how matter behaves. The absence of a deeper everyday picture may be unsettling, but it also illustrates the uniqueness of quantum properties. And while we may not have a fully intuitive image of spin, our ability to measure and use it is unquestionable. From magnetic resonance imaging in medicine to the read-write heads of hard drives, technologies exploit the fact that electrons come with spin-borne magnetism. That reliability is what makes quantum oddities part of everyday life. Reality baked spin into its basic particles, and we've learned how to turn that immutable fact into tools. Spin is a compass needle attached not to an instrument but to the particle itself. Understanding how those needles behave open entire fields of science and engineering. This framework also helps explain the peculiar balance between predictability and uncertainty across the universe. Electron positions may blur into probabilities, but their spin values remain sharply defined. It's because of this dual character that physics can build stable technology from unstable foundations. Probability clouds don't prevent a magnet from pointing north because the magnetic side of the electron isn't probabilistic in the same way. That puts spin in a special category: unpredictable location, reliable orientation. Seen in this light, magnetism stops being a familiar background force and begins to look like a reminder that reality carries strangeness at its root. Every compass needle steady point, every magnetic stripe on a credit card, every electric motor's rotation, all of it ultimately comes down to something that cannot be pictured as ordinary motion. It comes down to a particle property that exists with no deeper, because we can label. Spin is, and that's enough. Yet this raises a natural curiosity. If each electron is its own tiny magnet composed of a north and a south, why do magnets in the larger world always display both poles together? Wherever we cut a magnet, both halves keep a north and a south attached. Why is it impossible to isolate a single magnetic pole on its own? That question points toward one of physics' boldest ideas. Magnetic monopoles, the unicorns of physics. Magnetic monopoles sit at the intersection of mystery and necessity in physics. They are imagined as particles that would carry only one magnetic pole, a north without a south, or a south without a north. On paper, they solve neat puzzles about why charges come in fixed amounts and restore an elegant symmetry to how we describe electricity and magnetism. But in practice, they have proven stubbornly absent, which is why physicists call them the unicorns of their field. Every magnet we know splits itself into two poles. Slice a bar magnet in half, and instead of producing a lone north and a lone south, you get two smaller magnets, each complete with both poles. Split again, and the pattern repeats without end. No matter how deep you go, magnetism regenerates the same two-sided rule. The idea of a true isolated pole, just a magnetic charge like electricity has, remains hypothetical. In 1931, Paul Dirac showed why that idea was so enticing. He proved mathematically that if even a single monopole exists somewhere in the universe, it would require electric charge to come only in discrete steps. That's exactly what we observe. No one has ever measured half an electron's charge or a third of a proton's charge. All charges we see are neat multiples of an elementary unit. Monopoles, Dirac realized, would turn that observation from a mysterious fact into a natural consequence. His equation, called the Dirac quantization condition, binds magnetic charge to electric charge in a way that explains their balance. That link gave researchers a powerful reason to believe monopoles might be real, even if nobody had found one. The hunt has spanned decades. Collider experiments like MODO at CERN and cosmic ray observatories have searched for monopole signatures, each in their own way. Collider detectors look for unusual tracks from high-energy collisions, seeking particles that interact far more strongly with magnets than anything else we know. So far, these tests have set strict limits on the possible charges and certain mass ranges monopoles could have, but no confirmed events. Cosmic ray arrays, by contrast, scan the sky for rare, slow, and massive objects that could drift through detectors and leave behind unmistakable signals. These experiments have placed limits on how many monopoles can exist per square meter passing through Earth. In other words, if they're out there, they're either very scarce or far heavier than we can currently produce or capture. While fundamental monopoles remain missing, Physicists have found something remarkable in the laboratory. They can create magnetic behavior that looks like monopoles inside special materials. These are not the elementary Dirac monopoles imagined in 1931. Instead, they are emergent quasiparticles, collective excitations in carefully structured crystals. One of the best-known systems is spin ice, where the atoms line up in frustrated configurations that prevent every spin from satisfying its neighbors. The frustration causes some excitations to behave like isolated magnetic charges. In effect, one patch of the crystal behaves like the north pole of a magnet with no south in sight, while somewhere else the complementary south is displaced. The result is monopole-like objects that can move independently through the material as if they were free particles. In 2024, researchers added another example. Using quantum-sensitive magnetometry, they observed monopole-like excitations in hematite, a very common iron oxide mineral. Unlike the crystalline spin ice systems, this antiferromagnetic structure produces monopoles in a new way, making them easier to detect and control. Importantly, these emergent monopoles are not fundamental particles. They are collective disturbances, patterns of spin rearrangement that act like particles even though they are not made of matter on their own. But for practical purposes, they let experiments probe exactly the kind of magnetic charge physics that would be expected if real monopoles existed. These quasiparticles have already sparked applied research. Because they can behave like currents of magnetic charge, scientists are exploring whether they can transfer information in materials using far less energy than ordinary electron currents. Concepts such as racetrack memory hinge on the idea that streams of emergent monopoles could carry bits of data as mobile topological states. It's still early, and nothing is yet translated into commercial technology, but the fact that researchers are designing devices around monopole analogs shows how fertile the concept has become. Physics, once thought confined to elegant equations, is now driving practical engineering conversations. At the same time, the theoretical appeal continues to push searchers in more extreme regimes. Some proposals suggest that high-energy heavy ion collisions could finally provide conditions hot and dense enough to create monopoles, testing masses up to the TV scale. Others propose combing through ancient terrestrial minerals for trapped monopoles that might have fallen to Earth long ago during cosmic events. The range of approaches, giant colliders, deep-ground mineral samples, orbital cosmic detectors, underscores how valuable an actual discovery would be. If monopoles were ever confirmed, they would bring symmetry to Maxwell's equations, the cornerstone formulas of electricity and magnetism. As they stand, those equations show charge for electricity but not for magnetism. Add monopoles, and suddenly the two forces mirror one another. That symmetry would make electromagnetism look mathematically complete, reinforcing why so many physicists think monopoles should exist in principle, even if they've yet to appear in practice. That symmetry, combined with Dirac's link to charge quantization, keeps attention on the search. Still, it is vital to draw the line clearly. No experiment has yet captured a fundamental monopole. The best evidence we have are emergent quasiparticles and materials. Those are real, measurable, and repeatable in the lab, but they are not cosmic building blocks. They are puzzles of the condensed matter revealed when atoms are arranged in special geometries. The distinction matters because a true magnetic charge would alter our entire framework for describing the universe, while the emergent kind just gives us a sandbox to practice playing with the rules. Physicists often phrase it this way: emergent monopoles are costumes, convincing ones, but the actor inside is the material itself, not a particle from outside our equations. Yet these costumes are already teaching us. By interacting with quasi-particle monopoles, researchers can explore how magnetic charges might move, scatter, and store energy. The behavior is close enough to theoretical monopoles that experiments can even test which predictions hold steady and which assumptions falter. In a field where the actual particle might remain out of reach for decades, those laboratory stand-ins matter enormously. They offer a way to learn how monopoles might behave if they ever manifest fully in nature. So the picture today sits in a careful balance. On one hand, collider experiments and cosmic detectors have so far reported no confirmed sightings, while theoretical arguments remain stubbornly persuasive. On the other hand, emergent monopoles in crystals and minerals provide tangible, controllable systems that mimic the desired properties almost perfectly. Between these two realities, one hypothetical, one engineered, lies a frontier where symmetry, technology, and imagination collide. And this frontier is not just about abstract physics or exotic materials. For many living creatures, magnetic fields are not hidden mathematical curiosities at all. They translate into direct sensory information as natural and useful as vision or smell. Animals that can see the invisible. Some creatures don't just survive inside Earth's magnetic field, they use it as part of their everyday senses. This ability is called magnetoreception, and it shows up across the animal kingdom. Birds, turtles, fish, insects, and even mammals have evolved ways to detect magnetic cues that are completely invisible to humans. For them, magnetic information is not abstract. It's integrated into how they move, orient, and even find their way back to familiar places after years away. Birds are the clearest example. The European robin, a small songbird famous for its seasonal migrations, carries a retinal protein named cryptochrome 4, Cry4a, that appears specialized for magnetic sensitivity. Light triggers chemical reactions inside cryptochrome molecules, generating radical pairs of electrons whose states flip in ways influenced by faint magnetic fields. This so-called radical pair mechanism is finely tuned to the weak field generated by Earth itself. Migratory birds express more of the sensitive cry-footberry, a variant of non-migratory species like pigeons or chickens, suggesting evolution sharpened their ability for long journeys. In practice, it means that for the robin, magnetic orientation becomes part of its standard vision. The magnetic lines overlay its normal view of trees and terrain, giving it stable bearings while traveling across continents. Sea turtles show the magnetic map in an entirely different way. Newly hatched loggerhead turtles rush from their natal beaches into the ocean and, during that critical swim, register a specific magnetic signature that acts like a permanent address. Decades later, after traveling thousands of kilometers across ocean basins, females return to the very same stretch of sand to nest. A 2025 University of North Carolina study confirmed that loggerheads aren't just born with this instinct. They can actually learn and memorize field signatures associated with foraging sites, then recall them. This was the first experimental evidence for memory-based magnetic mapping in turtles, proving that their compass sense is not limited to innate behavior, but extends to learned navigation. Navigation tied to the field goes beyond vertebrates. Insects provide striking cases. Fruit flies lose much of their orientation ability when their cryptochrome genes are altered, showing that even the smallest organisms make use of the same radical pair chemistry found in birds. Honeybees and stingless bees also navigate with magnetic help. Experiments with the Brazilian stingless bee revealed that the antennae are covered in thousands of tiny hair-like sensilla that act as magnetic sensors, channeling information directly into the nervous system. These delicate structures steer foraging flights and homing behavior, ensuring the bees return reliably to their hive. Fish exploit the field as well. Salmon orient their migration routes according to Earth's magnetic patterns. Controlled tank experiments shift the field conditions artificially, and the fish adjust their swimming direction accordingly, even though no physical landmarks change. This shows that they continuously sample magnetic cues as part of their orientation. Stingrays offer an especially advanced example. The yellow stingray has been shown to detect differences in both the angle of magnetic field lines and their strength. For such animals, the field is not just a compass, it provides detailed positional data, like a built-in map overlay. Even mammals appear quietly influenced. A large analysis of satellite images and on-ground surveys suggested that when cattle graze freely in open pastures, they tend to align their bodies along north-south axes more often than chance would predict. No fences forced this arrangement. The conclusion was that magnetic alignment may provide subtle benefits to physiological comfort or orientation. It demonstrates that magnetoreception doesn't have to appear only in dramatic migrations. Sometimes it emerges in routine postural behavior. The mechanism of magnetoreception varies among species. Cryptochrome-based detection works best in daylight and involves quantum chemistry in the eyes, but another pathway appears to exist in some birds and other vertebrates. Small deposits of magnetite, an iron-based mineral, have been proposed inside tissues such as the upper beaks of pigeons. These deposits might mechanically tug on receptor cells connected to the trigeminal nerve, sending direct physical signals to the brain when they shift with the field. Such ion-based systems would function even in complete darkness. Unlike the light-dependent cryptochrome system, evidence suggests that both cryptochrome signaling and magnetite detectors may coexist in particular animals. For example, pigeons might rely on their eyes during the day, but also preserve an iron-based backup for cloudy or nocturnal conditions. Evolution appears to have produced dual strategies with redundancy that ensures orientation never fully fails. The sensitivity of these systems is remarkable. Some research suggests that cryptochrome-based magnetoreception operates near the quantum limit of magnetic detection, meaning animals may be working close to the very boundary physics allows for sensing weak fields. That doesn't mean birds perform lab-style precision metrology. Instead, it indicates that evolution has driven their biology to the edge of what quantum rules permit. That extreme precision also has a consequence. External interference can disrupt it. In lab settings, weak background radio frequency noise from urban wiring sometimes jumbles birds' compass orientations. Something as ordinary as stray electromagnetic chatter from a streetlight can throw off a robin's built-in compass, underscoring how delicate the mechanism is in practice. Put together, these findings reveal just how widespread and flexible magnetoreception is. Amphibians, reptiles, fish, insects, and mammals all show evidence of it. Each species uses the same global field differently, depending on its needs. Migratory birds adjust course over vast distances, salmon return to distant rivers, turtles resurface where their life began, and bees calculate field direction while visiting flowers nearby. For cattle in a pasture, the benefit may be comfort or stability. For each, magnetic information is not an abstract background detail. It has been integrated into biology as a tool for survival. For humans, though, this remains largely hidden. We can measure fields with instruments, but we lack a direct perception of them. What's clear is that other life does not share that blindness. They tap into the constant geomagnetic web and navigate by it with a fidelity we can only approximate with our devices. Their reliance shows that magnetism is not only a backdrop for physics, it is also a fundamental ecological presence shaping behavior across entire branches of evolution. Of course, we compensate in different ways. Since we cannot sense Earth's magnetic framework directly, we embed artificial magnetism into our tools. From navigation devices to consumer electronics, we build engineered versions of what animals carry in their heads. And that leads to an unexpected truth waiting much closer to home. Even the object you reach for dozens of times a day relies on magnetic principles more deeply than you might think. Magnets in your pocket supercomputer. Magnets are not just guiding turtles or bees, they are engineered into the phones most of us carry every day. Modern smartphones quietly depend on magnets in almost every core feature. Open one up and you wouldn't find just a single block of metal. You'd discover multiple rare earth magnets tucked into different components. They don't hang around as an optional extra. Without them, the device would make sound, vibrate, stabilize its camera, or charge wirelessly. Start with the speakers. The thin grills at the edge of your phone hide neodymium magnets, prized because they're the strongest permanent magnets for their size. An electrical signal drives a coil against one of these magnets, which moves a flexible diaphragm. Every sound, whether a voice on a call or music from your playlist, emerges from that push and pull. The microphones inside work the same principle in reverse. Incoming vibrations shift the diaphragm, which interacts with a magnet and coil to generate an electrical signal. Both hearing and speaking through your device depend on these small invisible fields. Even the vibration motor, the haptic system that gives you feedback when typing or receiving alerts, relies on magnets. Instead of turning gears, a magnetic setup inside shifts a small weight rapidly when current flows, creating sharp pulses or longer buzzes you can feel in your hand. Engineers prefer this design because it fits in impossibly thin spaces, costs little energy, and works reliably without mechanical wear. Cameras highlight the importance of precision. Shaky hands normally blur images, yet smartphones stay sharp thanks to magnets managing optical image stabilization. Inside the lens assembly, the sensor or lens element sits suspended on springs. Multiple tiny neodymium magnets correct for movement by nudging the lens or sensor in the exact opposite direction of the shake, often just a fraction of a millimeter. Snapshots in dim light or videos recorded while walking stay clear and steady, only because those hidden magnets constantly adjust in real time. Wireless charging offers another reminder. Beneath the back casing, a coiled wire waits for induction energy. But for induction to work efficiently, the phone and charging pad must align properly. To guarantee that alignment, small magnets pull the two coils into position. That click of placement you feel when setting the phone down is the magnets guiding the energy path. Without them, charging would waste power or stall when the device slipped a few millimeters out of line. Zooming further out, the number of magnets in a single smartphone may only be several, but their strength and precision outweigh their size. Each is manufactured from rare earth alloys, commonly neodymium iron boron, chosen specifically because they deliver powerful magnetic fields in the thinnest possible dimensions. Internal layouts allow almost no wasted space, so only the strongest compact magnets can make those features viable. There's a cost that extends beyond the device in your hand. Rare earth supply is not spread evenly across the globe. Processing of these elements is concentrated, with China dominating the refining and magnet production. Chain, around 90% of output by some counts. That concentration creates risks. Disruptions in trade, shifts in regulation, or export controls could tighten supply, which in turn raises costs for manufacturers and constrains how quickly new design can scale. The phone's hidden magnets connect directly to one of the world's most centralized supply chains. This tension is why recycling gains so much attention. Toss an old smartphone, and you are also discarding rare earths that were mined, refined, and built into precise shapes. Recycling offers a way to reduce that loss. The e-waste recycling industry generated about $28.1 billion in revenue in 2024, and it continues to grow year by year. Beyond reducing landfill, the industry now focuses specifically on extracting rare earth magnets from electronics like hard drives, EV motors, and mobile devices, feeding them back into the production cycle. Technologies for recovering the magnets are developing quickly. Some companies are scaling hydrogen-based processes that can loosen magnets from their assemblies, allowing them to be recovered with less damage and less energy. One commercial group is planning to bring such a short-loop plant online in the United States. Academic laboratories explore complementary approaches. At Texas A&M, researchers are testing mesoporous carbon materials for selectively pulling rare earth ions out of crushed electronics. Each of these efforts aims at creating cleaner, more effective ways to reclaim magnets that otherwise remain locked inside abandoned devices. IT asset disposition companies have also widened their responsibilities. Beyond wiping data and reselling functioning hardware, many now specialize in disassembling bulk electronics for critical material recovery. Magnets from obsolete servers, laptops, and phones are cataloged as assets worth capturing, not junk to be disposed of. Step by step, this builds a circular chain where rare earths re-enter manufacture instead of being replaced by fresh mining. Smartphone design trends point toward even greater dependence. Foldable models use miniature magnets and hinge systems alongside the boosted demands of larger speaker modules and multi-sensor camera arrays. Strong magnets also appear in add-on accessories, from detachable earbuds to wireless wallet attachments that snap into place by magnetic grip. As features expand and internal layouts shift, adding magnets provides solutions that are both compact and reliable. That means a future flagship will house even more magnetic components than the standard phones of today. So the technology is balanced on both chemistry and geopolitics. Magnets give us incredible functionality in small devices, but their material base comes from elements hard to substitute and difficult to source sustainably. Recycling and innovative recovery methods stand as critical answers, not just to reduce waste, but to secure continuity of supply. In this sense, a smartphone represents the crossroads of advanced physics, consumer electronics, and global industry. Its ability to connect people rests partly on how carefully we manage the same rare earths that keep its speakers talking and its camera steady. Magnets in phones reveal how a hidden physical force underpins our everyday tools. They turn the invisible into the practical conversions of sound, touch, image, and energy. Engineers channel these fields through wire coils and housings so naturally that the technology feels seamless, even simple. Yet each magnet has been placed deliberately, tuned for strength, and paired with global networks of mining or recycling far removed from day-to-day use. The world in your pocket is stitched together with precise alignments of rare earth materials that remain among the most contested and essential resources we have. This is only one corner of what magnetic engineering makes possible. The same force shaping signals in a phone also operates at scales much larger than your hand. In fact, entire transportation systems and experimental physics projects now rely on magnetic designs that look far closer to science fiction. Quantum trains and floating wormholes. Magnets no longer sit quietly inside devices. We can now step onto machines that show what control fields can really do. The most striking current example is the magnetic levitation train. Unlike conventional rail cars grinding along wheels and tracks, these trains rise just above their guideways, supported entirely by electromagnetic force. There is no physical contact, only a cushionless glide of metal held steady in midair. Removing wheels eliminates the issue of friction, the enemy of speed. Bearings don't wear down, noise and vibration vanish, and nothing drags against steel rails. The absence of rolling resistance means the limit is no longer set by what wheels can withstand, but by how efficiently fields can be arranged and how much air resistance the train must overcome. Commercial Maglev systems already cruise at over 300 miles per hour, more than double the fastest commuter trains in the United States. From the passenger's perspective, it feels almost weightless. Acceleration builds cleanly, the ride is smooth, and you arrive before you expect. China has invested heavily in stretching these numbers further. The T-Flight program combines traditional maglev lift with sealed tubes operating at reduced air pressure. In ordinary conditions, as velocity rises, drag builds until it dominates propulsion costs. Remove much of the air, and the train cuts through far more efficiently. This design has already reached several hundred miles per hour in controlled tests. Long-term plans aim at much higher speeds, even competitive with aircraft. Remaining routes like Beijing to Shanghai might shrink from nearly 5 hours by rail to under 2. Importantly, these remain targets today. Prototypes show the feasibility of the approach, while scaling to commercial service requires solving both cost and reliability challenges. Japan's approach relies on a different advantage: superconducting electromagnets. The L0 series maglev has already clocked 374 miles per hour in trials and is projected to carry passengers on the Tokyo-Osaka line by the 2030s. These trains depend on supercooled coils that allow current to circulate indefinitely without electrical resistance. Once the field is built, the magnets maintain their strength with very little power input, making them efficient over time. But this technology is difficult to run. The cryogenic cooling is complex and costly. Still, the payoff is enormous. The trip between Tokyo and Osaka, usually close to 3 hours, should be cut to just over 1. Commercial maglev trains are not limited to these two programs. China's Shanghai maglev has been operating since 2004, carrying passengers at a steady maximum of 268 miles per hour between the airport and the city. South Korea also runs urban maglev systems, though at lower speeds, showing that the technology can serve everyday transit, not just experimental showcases. Each example demonstrates that levitation can already be applied at scale, but also reveals why global adoption moves slowly. It requires infrastructure uniquely designed around superconducting or electromagnetic tracks. In the United States, feasibility assessments continue, but construction rarely breaks ground. The financial barrier is daunting. Cost estimates fall between $50 million and $200 million for each mile of track, a figure much larger than for conventional railroads. Yet advocates point out that once the systems run, their day-to-day costs should drop dramatically. Tracks face far less wear, maintenance needs shrink, and operations could be as much as 70% cheaper than traditional setups over the long run. The mismatch is clear: enormous initial investments set against attractive reductions in lifetime expenses. That dynamic keeps maglev stuck between technical success abroad and budget deadlock at home. While these trains represent the large-scale, practical side of magnetic engineering, superconductors have opened far stranger possibilities in physics laboratories. In 2024, several groups tested structures that made magnetic flux behave in ways unlike anything seen in ordinary materials. By arranging superconducting shells and ferromagnetic layers, they created magnetic tunnels where field lines vanish at one point and resurface intact at another. The effect looks like invisible transport of the field. Some researchers describe these as wormhole analogs, an analogy, not evidence of space-time distortions, but a vivid way of expressing how flux can be hidden and then guided to reemerge elsewhere. The underlying mechanism comes from the special properties of superconductors. Below a critical temperature, they conduct electricity without resistance and expel external magnetic fields, an effect called the Meissner effect. In addition, flux pinning allows certain field lines to anchor inside the material, letting engineers suspend magnets above superconducting tracks or channel flux through control pathways. These traits enable levitation for trains, but also allow laboratory demonstrations where magnetic signatures can be cloaked or redirected. The practical value of these proof of concepts is still uncertain, but the physics is solid. In principle, devices could be designed to shield sensitive instruments from outside fields, produce invisible magnetic conduits between regions, or build new types of magnetic circuits distinct from conventional wiring. These are not teleports or science fiction portals. They are carefully designed electromagnetic effects that behave like analogies to wormholes, without stretching into claims about space-time itself. Taken together, the contrast is striking. Maglev trains represent the most visible success, vehicles moving faster than airplanes, enabled entirely by controlled electromagnetism. Laboratory flux experiments show the opposite side, abstract manipulations where invisible forces are steered through space in ways that appear almost magical, though strictly grounded in material science. Both rely on the same fundamental principle, that strong superconducting magnets let us manage fields with unusual precision. Engineering around magnets now points in two directions, toward global networks of near-frictionless transport and toward experimental devices that give us deeper tools to explore basic physics. Infrastructure and laboratory are linked by the same underlying field, manifesting at scales from mass transit to isolated experiments. As research continues, the lines between engineering, efficiency, and curiosity blur, because the same technology that keeps commuters moving can also inspire techniques to manipulate fields for shielding or sensing. Magnets here are not decorative extras. They embody the principle that control over fundamental forces reshapes both travel and scientific curiosity. The same invisible threads that raise a train above its track also allow an experiment to conceal a magnetic field. That kind of dual purpose, practical and conceptual, is rare in technology and suggests the reach of electromagnetism extends further than most everyday experience allows. Yet for all these achievements, magnets have an even older role, one we live under constantly whether or not we notice it. It operates not in passenger trains or laboratories, but across the entire planet. And as steady as it seems, even that planetary field can change dramatically. The looming fear of magnetic pole reversal. What if Earth's compass quietly shifted so that North and South traded places? It sounds like something from science fiction, but it's a natural process the planet has gone through many times before. This phenomenon is called a geomagnetic reversal. Geological records show that throughout Earth's history, the magnetic poles have switched direction again and again. The evidence is written into volcanic rocks. Lava cooling at the surface locks into magnetic field's orientation, like a tape recording of Earth's polarity at that exact moment. By sampling rocks from across the globe, scientists have built timelines showing that reversals are not rare accidents. They are recurring events imprinted into crust itself. Still, there is no fixed pattern. While the long-term average works out to roughly 4 to 5 reversals per million years, equivalent to one every 2 to 300,000 years, that number varies wildly. Sometimes reversals occur relatively close together, and other times the field can stay stable for tens of millions of years. During the Cretaceous period, for example, Earth went nearly 40 million years without a single flip. By contrast, in the past 10 million years, reversals have happened more frequently. The message is clear: these events don't follow a metronome. They appear unpredictably, sometimes clustering, sometimes pausing. Where we are today adds intrigue. The last full reversal, the Bruns-Matsuyama event, happened around 750,000 to 780,000 years ago. If you compare that to the rough average, you might conclude Earth is overdue, but this framing can be misleading. Because reversals are irregular, using an average like a countdown clock doesn't work. Past intervals stretch anywhere from tens of thousands of years to tens of millions. Some models have attempted to project that, at the present rate of field weakening, a flip could occur within the next 1,000 to 2,000 years. But geophysicists caution against taking those projections at face value. Reversals are not linear. Sometimes the field weakens and then recovers, producing temporary excursions rather than full flips. For example, the Lachamps excursion around 41,000 years ago saw the field collapse and partially reverse, only to rebound back into its current alignment. That variability makes exact predictions unreliable. If a reversal does occur, it won't happen overnight. Unlike a light switch, the Geodynamo takes thousands of years to reorganize. During that time, the poles wander, sometimes moving toward the equator before stabilizing in swap positions. The field weakens during transitions, dropping to perhaps 10 to 20% of its normal strength, creating centuries of reduced shielding. For anyone relying on a compass, it would mean slowly shifting directions, drifting toward unreliability before eventually resettling north and south in reverse. For us, the process would unfold gradually enough to be noticeable over generations, not mornings. Even now, researchers are paying attention to signs of unusual behavior. The North Magnetic Pole, once drifting slowly through Canada, surged in speed during the 2000s, covering around 55 kilometers per year before easing back to about 35 kilometers annually in recent years. That acceleration was unprecedented in the era of precise measurements, and it forced more frequent adjustments to global navigation models. Meanwhile, another long-studied anomaly is the South Atlantic anomaly. Stretching from South America across the Atlantic, it marks a region where the magnetic field is weaker than expected. Satellites passing through have reported malfunctions, as the weaker field allows more high-energy particles from space to penetrate the atmosphere. What deepens the concern in 2025 is the emergence of a second weak zone developing off the coast of South Africa. With two connected anomalies under watch, scientists are carefully monitoring whether these patches signal the onset of a larger global change. At present, no one can say for certain. The anomalies could stabilize, split, or simply continue migrating. What is clear is that field behavior today is unusual compared to centuries past, and that makes the question of reversal feel less abstract. But even if the field is changing, what would the consequences actually be for life and technology? Here the story becomes less catastrophic than popular imagination suggests, though not trivial either. Life on Earth has passed through thousands of flips without collapse. The fossil record shows no mass extinctions triggered by magnetic reversals. That said, the challenges today would be new because of how dependent human society is on electronics and satellites. Orbiting satellites are particularly vulnerable. A weakened field would expose them to higher levels of solar and cosmic radiation, potentially damaging onboard circuits and shortening operational lifespans. But the outcome is not instant, and it isn't guaranteed collapse. With monitoring, engineers would design satellites with additional shielding or plan for faster replacement cycles. Similarly, global navigation systems like GPS would not suddenly fail, but they would need more frequent recalibration as magnetic reference models shift during extended periods of field instability. On Earth, the biggest risks lie in the interaction of geomagnetic storms with power infrastructure. Already today, strong solar storms occasionally induce currents in electrical grids. These extra currents can overheat transformers, disrupt communications, and cause localized outages. With a weaker field, the same storms could drive stronger surges further into the grid, magnifying the effect. But advanced warning systems and deliberate engineering, using surge protectors, resistant transformer designs, and alternative routing can greatly reduce the chance of catastrophic blackouts. The risks increase, but they are not unmanageable. Aviation would also feel the impact. Flights over polar regions, which already encounter heightened radiation during solar storms, could face higher levels. Airlines might shift routes to lower latitudes or altitudes during peak activity, increasing fuel use and flight time but preserving safety. These adjustments would inconvenience operations, but they reflect ongoing adaptation rather than crisis. The biological world, however, has a different challenge. Many migratory species, including birds, whales, sea turtles, and butterflies, use Earth's magnetic field as a guide. When the field weakens or becomes unstable, these creatures may misinterpret cues. Scientists suspect this could cause temporary disruption during migrations, increasing mortality rates until species adapt. Over evolutionary timescales, life has proven remarkably resilient to these shifts. But in the short term, decades to centuries, the disarray could be significant. A world experiencing a reversal would likely see confused migrations and gradual retraining of instincts across generations. So are we standing at the edge of another flip? The only honest answer is that it's unclear. Signs of a weaker and more complicated magnetic field exist, and anomalies like the South Atlantic anomaly and its new companion region highlight unusual dynamics. But the geologic record shows reversals are not predictable in human terms. They may happen sooner, much later, or not at all within the next 100,000 years. Excursions muddy the record further, showing that near reversals can resolve without flipping fully. That uncertainty explains why scientists track the field so closely with international models like the IGRF and WMM, updated every 5 years. These are not predictions of when a reversal will occur, but tools for keeping navigation, science, and industry accurate in a constantly shifting environment. If and when a reversal comes, it will not be an instant collapse. Instead, we would face centuries of adjustment, navigational models updated more frequently, satellites hardened, grids reinforced, and species challenged to adapt to new cues. Humanity would respond with the same resilience that allowed countless generations of life to persist through previous flips. A reversal represents reorganization, not extinction. The Geodynamo doesn't stop, it reorients. North becomes south, south becomes north, and eventually strength returns. Understanding that distinction matters. It reframes geomagnetic reversal not as a global disaster waiting to strike, but as another expression of how restless and dynamic Earth truly is. It is a test of adaptation, both technological and biological, forced upon us by the physics of the planet's interior. And whether the next reversal comes in 1,000 years or far further in the future, it reinforces the larger lesson this journey through magnetism has revealed. These hidden forces not only shape daily life and technology, but they also remind us that the universe's most enduring structures often lie beneath notice, only surfacing when they change. Magnetism ties together some of the most important aspects of our world. It protects Earth with a global shield, helps animals chart migrations across oceans, and powers the devices in your hand. The same physics links compass needles to superconducting trains and to the neodymium magnets buried inside your phone. In 2025, scientists are still uncovering new possibilities. Emergent monopole-like excitations in materials, quantum-engineered structures for sensing, and improved global field models for navigation. A true fundamental monopole would have deep theoretical consequences, but so far only emergent versions in special materials have been observed. Which of these magnetic facts surprised you most? Drop a comment and subscribe if you want more science and mystery made clear.